forgot to add a little addendum for those of you who are interested, because some of you may have asked yourself, why? Why does cyclobutene open thermally conrotatory and go back disrotatory with light, and the opposite with hexatrine and so forth? And the explanation is really advanced organic chemistry, but I'll give you an inkling of it. It has to do, perhaps for the first time that you're seeing this explicitly, with the sign of the wave function of the reacting orbitals. Now, when you look at what reacts in all of organic chemistry, it's the so-called frontier orbitals, meaning the highest lying orbitals are where the action is. This is sort of related to Chem 1, atomic theory. Atoms react with the valence electrons, right? The inner shell electrons are not used. It's always the outside ones, the ones that are most weakly held by the nucleus. So that makes sense. They're the most reactive. If you look at organic systems, we have all these orbitals. The highest lying filled ones are the ones that are responsible for most of the action. Okay? And the way you determine, of course, this is just like in the atomic theory, you determine where they lie, actually exactly by numbers, is you measure the ionization potential. So you fire some beam at it, and you measure when the electron gets blown out, and there's an energy associated with that, and that's where these lines come from when we draw these levels, orbital levels. Okay? So in the case of butadiene, in the case of ethylene, we had two levels, the bonding molecular orbital, anti-bonding molecular orbital. Okay, the bonding was filled. For butadiene, we have two more, so 4 p orbitals turn into 4 molecular orbitals. So it's 2 bonding levels and 2 anti-bonding levels. And so we have a distinction between a lower bonding level and a higher bonding level. And the molecules react out of the higher bonding level. And when you look at the differences between all these levels is that the lowest filled orbital, has no nodes. So all of the orbitals are lined up such that all the pluses are next to each other at top and all the minuses at the bottom. The next higher one has a node. Okay? And that's the one that reacts because it's the highest filled orbital. And that node is shown in here. So this is for the first and perhaps only time where the color of my orbitals here signify charge. Okay? So if blue is plus and green is minus, notice there's a node in the molecule right in the middle. Okay? So that's the highest, the higher level occupied orbital. Okay? And you will notice that because of this node, this one is plus and this one is minus. So when you want to make a bond between the two carbons that I hold in my hands in a ring closure reaction, this is the notion that brings plus on top of plus to give a bonding interaction. Okay? So it has to rotate conrotatory in order to do this, either that way or that way, minus and minus, but it has to be a reinforcing interaction. That's why they rotate the way they do. Now, interestingly, and this falls out of the symmetry of the molecules in the calculations when you calculate the orbitals, in the butadiene case, the next higher orbital is now unoccupied. But when you photolyze, the electron goes into a higher level and falls into the lowest, at that stage, empty orbital, which is the next higher orbital. So that's the third orbital. And so this one has one node, that orbital has to have 2 nodes. And here it is. The 2 nodes are here and here. And now if you look at the end pieces, you notice that the symmetry is such that now the 2 blues are on top and the 2 greens are at the bottom. So in order for bonding to occur, it has to go disrotatory. Okay, so it's a matter of which is the frontier orbital that determines which way these guys rotate. And if you do the same game for hexatrine, it just inverts because you're adding another double bond, so all the numbers, the pluses and minuses, extend and switch around, okay, such that the highest level, occupied level, is now blue on top for hexatrine, and so for the thermal reaction it goes disrotatory. And then the next level that is populated on photo excitation has this scenario. Okay? That's why this is so. Okay, so now let's move on to one of the most interesting polyenic systems, namely a cyclic system, and then we'll look generally at polycyclic olefins. And this is a character that we've seen already briefly when we talked about hexatrine, namely when we asked the question, is there something special perhaps when you take hexatrine and close it and take away 2 hydrogens, of course, to make a cyclic hexatrine or cyclohexatrine. And that gives rise to this beast here, which you notice already is rather special because it's completely symmetrical. And that guy is called benzene. And this was discovered in 1825, more or less, when Michael Faraday was walking the streets of London, and he noticed that in the street lights, the London streets in those days were lit by candles, essentially, fueled by whale oil. Okay, so in those days they used whales to light the streets of a city. The environment had not been invented yet, and cancer didn't exist. And he noticed that there was this liquid dripping down that didn't burn as fast, I guess, and he was curious, and he looked at it, he touched it, it has a sort of gasoline-like little bit smell, and he started investigating it. And he found very quickly that the elemental analysis gave an equal number of carbon and hydrogens, eventually established to be C6H6. If you look at the molecular formula C6H6, clearly there's unsaturation in there, there has to be double bonds in there. Yet, the molecule didn't react with HCl, HBr, was stable to air, it was unusually unreactive. It took 40 years before Kekulé, German-Frenchman chemist, postulated the cyclic structure, and he postulated that there's something special about the cyclic structure of such a trine. Okay? Here's actually the original Kekulé model as it exists at the University of Darmstadt. I took a picture of it, and you notice that he postulates still alternating double and single bonds, but this didn't conform with the chemistry of this material, because if this were the actual structure, one would postulate that there are 2 isomers of, say, a dibromo benzene where the 2 bromines are next to each other, namely one isomer where they're linked by a double bond, and another isomer where they're linked by a single bond, and that didn't exist. Couldn't be found. So he then proposed, in a brilliant move, a preview of resonance, really, at a time when they didn't even have any spectroscopy, and they didn't even know what electrons were and where they were sitting, that the atoms must be moving around. And he said it's quite feasible that in a cyclic structure like this, when they start rattling around such that these 2 carbons get closer together, this means that these 2 carbons and these will get further apart. And if you do this in a sort of concerted manner all around the molecule, then double bonds and single bonds should trade places. In other words, it will equilibrate to what is de facto a resonating structure, even though he didn't say that, he called it oscillating. And in modern resonance, of course, we show it as the two resonance forms that are equivalent. And remember, when we have two or more equivalent resonance forms, this is an especially stabilizing kind of arrangement. Benzene has a long history. There are stamps. In Belgium, there's a stamp commemorating Kekule. There's this picture in the benzene ring. This is a picture of what was envisaged to be the origin of either that or some monkeys biting their tails. The lore has it that Kekule dreamt this as he was thinking day and night about what could be the structure, that it came to him in a dream. Well, this is sort of shaky. But my students say it was probably an attack of reefer madness that did it. But this is, this perhaps is, in my perspective, not such a big leap, but the fact that he recognized this kind of oscillation resonance type thing is really quite brilliant. So before we go on, let's look at nomenclature. And that's very simple. Benzene is a hydrocarbon, so it falls into the hydrocarbon groups. There's nothing special about it. So any substituents to it are labeled as substituents. Okay? So alkyl groups, halogen groups, nitro, and so forth are labeled as such. So this one, for example, is a fluorobenzene. This is nitrobenzene. The rules for complex substituents, chapter 2, still hold. So tertiary butyl by IUPAC is really 1,1-dimethyl ethyl. Okay? There is one additional twist that is sort of special, is historical. When you have a disubstituted benzene, there are three possible ways of putting the substituents onto the ring. One is neighboring, 1,2, IUPAC would call this, but very common nomenclature is ortho, or short O. Okay? So we'll use ortho colloquially. If they are 1,3, IUPAC will call it 1,3, then they're called meta. If they're 1,4, they're called para. And we will all often refer to ortho, meta, and para attack in the next few lectures to come, meaning that looking at this molecule, ortho attack would be here, meta attack would be here, para would be here. By IUPAC, this guy is straightforward 1,2-dichlorobenzene. Okay? And exam questions, only IUPAC. This guy is straightforward. It's 1,3. The only choice here is which one is 1 and which one is 3. Okay, and there the golden alphabetical ordering rule takes over. Okay, so the alphabetically bromo is in front of nitro, so that therefore bromo gets the 1 and nitro gets the 3. And similarly here, this is 1-ethyl, 4,1-methyl ethyl benzene because E is before M. Okay. Now this you don't have to remember, except that I wanted to tell you that all other benzene derivatives, as soon as they have a function on them, and that's true for alkanes too. So benzene has no special place in the nomenclature. It's just like an alkane. Once you have a functional group, then the molecule is named after the functional group. So we learned that when we introduced alcohols. Alcohols were not hydroxy alkanes, they were alkanols, and you numbered accordingly and so on. Okay? So this guy has a hydroxy, so this one is not a hydroxybenzene, is strictly speaking benzenol, suggested by IUPAC, but is accepted by IUPAC, and we'll use it in the book. It's phenol because of tradition and history. Okay? So phenol itself is actually the active ingredient in sore throat sprays. For example, Chloraseptic. I'm sure most, if not all of you, have sprayed this down your throat when you had a sore throat. And it's phenol that does it. Okay? This one is benzenamine, not aminobenzene. Common name is aniline, but we'll use benzenamine. It's used in dye manufacture. We'll see how colored compounds can be made from compounds like this much later. This one is benzene carbaldehyde, short benzaldehyde. That one is actually the origin of almond flavor. This one is 1-phenylethanone. Common name acetophenone, is a hypnotic drug. Look how simple a structure this is, and it acts as a hypnotic drug. This is my rendition of a hypnotic drug. Okay? If you look at it long enough. Either that or the Immel movies, then you get totally woozy. And benzene carboxylic acid, short benzoic acid, all of you have ingested that because it's a very common preservative. And so it prevents molds on bread and stuff like that. So it's added to a lot of food. So if you haven't done so already, you should start from now on. Everything you buy, if you look at the label of the ingredients, you should read those things because you can now understand what's in them. And if you don't know what certain compounds do, you can look them up. Okay, the general term for benzene derivatives is arene. That's very colloquial, and so general for an arene substituent is arol. We might use this in a colloquial way. More significant is this. This is IUPAC, namely the benzene ring is a substituent, C6H5. It's called phenyl. Okay, so when the benzene ring is substituted on something larger, then we call it phenyl group. And similarly, so similar to when we had ethenyl or vinyl, okay, the double bond. This one is the benzene ring. And similar to the allyl system that has a special name, 2-propenol, that we introduced at the beginning of the semester, phenyl attached to a CH2 is, IUPAC will call it phenyl methyl, but it's got a common name, benzyl. So benzyl is the benzene equivalent to allyl. In allyl, it's a CH2 next to a double bond. In benzyl, it's a CH2 next to 3 double bonds that are in a cyclic array. So these things will pop up again, and I'll remind you of that kind of naming. And this you don't have to remember either, but the benzene, historically, benzene derivatives were given the term aromatic compounds because a large fraction of them obtained from nature were highly fragrant, had a great aroma. We will see in a minute that the term aromatic has been degenerated into meaning something totally different. But here are some aromatic benzene compounds. This guy here with a hydroxy and an ester is methyl salicylate, is the oil of wintergreen flavor. This one is vanilla flavor. That's what you use for, if you, instead of using the vanilla extract from nature, you can just make it industrially and generate tons of vanilla flavor that way. And this one is called thymol. It's a simple benzene derivative. It's the thyme flavor. Okay? So there are lots of these compounds. Okay, back to the structure. As you already saw in the molecular model, and it's implicated by the 2 resonance forms, the molecule is a regular hexagon. And all carbons are sp2 hybridized, 120-degree bond angles, and there's only one bond length because all 6 bonds are equal, and that bond length is, lies in between that of a normal double bond and a single bond, indicating that the pi electrons are delocalized. And here's the orbital picture. You can see all carbons are sp2 hybridized. They're all equivalent. And on this carbon, I did the whole picture where you see the 3 sp2 hybrids as they make bonds to the attached hydrogen and the carbon frame. The electrostatic potential map, as you might expect, shows a ball of red on top and actually a ball of red underneath. This is the top view. And if you look at the side, these look like sort of like a donut. Okay? A ball of electrons sitting above the carbon frame, above and below. Okay? And they are delocalized. They move around. It's like a wire, a circular wire. Okay, so why is benzene so unreactive? it looks as if it might have to do with the fact that it's unusually stabilized. And in this case, the stabilization translates also into lack of reactivity. Unlike butadiene and hexatriene, which were also stabilized by resonance, but we noticed that they actually were still quite reactive because the resulting intermediates, cations, radicals, what have you, were also stabilized by resonance. So how do we get at whether benzene is unusually stable? We use the old trick, the heat of hydrogenation. So we're going to hydrogenate benzene and get a number, and so we need to compare this number to something that we would have expected if there's nothing special about benzene, if benzene is actually a cyclohexatriene. So how do we go about that? First, we look at model compounds. So let's look at first cyclohexene. When we hydrogenate that, the heat of hydrogenation is 28.6 kilocalories per mole. Then we hydrogenate cyclohexadiene. The heat of hydrogenation of that is 54.9. Notice that this is not exactly 2 times that. 2 times that would be 57.2. Okay? But it's actually 2.3 kilocalories less. Why? Because, and we did that already for butadiene a couple of lectures earlier, because there's a little bit of delocalization around this, across this carbon-carbon bond, worth about 2.3 kilocalories per mole. For cyclohexadiene, therefore, we get 54.9 kilocalories per mole. And that's the resonance 2.3 is the resonance energy for a diene in cyclohexadiene. Now we can estimate from these numbers what we would expect if benzene is just a normal cyclohexatriene. We would expect 3 times a normal double bond, cyclohexene double bond, therefore 3 times 28.6, minus 3 of these resonance interactions, because we have 3 now, 1, 2, and 3, of the backbone of a diene type interaction, which is 3 times 2.3, so minus 6.9. We would expect 78.9. Now we do the measurement, and you find it's 49.3. So rather than sitting up there, giving us 78.9 kilocalories per mole, it's actually sitting here, giving us much less, 49.3. The difference is 29.6. Let's call it 30. 30 is the standard value that people throw around. And that's the difference in the heat of formation and heat of hydrogenation of benzene relative to a cyclohexatriene. So it's 30 kcals more stable than expected. And that's typically called the resonance energy of benzene. And in more modern terminology, it's called the aromaticity of benzene. So aromatic has now been subverted into a term that describes thermodynamic stability. 30 kcals is a lot. Okay? That's way more than the Weasley 2.3 kcals we saw of butadiene. That's a lot of stabilization, and that makes benzene not only thermodynamically stable, but kinetically stable, because reactions that occur on the benzene frame need to disrupt this cyclic delocalization, and that costs. Okay? It can be done, but it costs. Now, this special stability, called aromaticity, we've seen actually before also in transition states, and it applies to transition states that are unusually stabilized. And here they are. We've seen them before. This one and this one actually very recently, right? These are cyclically delocalized 6 electrons that benefit from aromatic stabilization, and this is one of the reasons that the Diels-Alder reaction is even possible. It's kinetically. Okay? Thermodynamically, we know it's possible because we can calculate the heat the bonds made, subtract the bonds lost. We know it's exothermic by 30 or so kilocalories per mole. But that doesn't mean that the reaction will occur readily. A good analogy is gasoline. Gasoline has an enormous heat content, and relative to CO2 and water, which it should convert to and does eventually in an oxygen atmosphere, it's hundreds of kilocalories uphill, up there, and it goes down when it burns. And the reason that it sits there and doesn't do anything is because the activation energy for burning, that is oxygen attacking, is way high. Okay? And so nothing happens at room temperature or even elevated temperatures. Indeed, in your car, you use the spark plug to get around that, right? Or if you want to accelerate the burning, you use a match. Okay? So it's the flame that then starts the fire, and then the fire is self-sustaining. But gasoline itself, is perfectly inert at room temperature. So this cyclic transition state really helps the Diels-Alder. Same thing here. Here's a cyclic transition state. 6 electrons in a cyclic array. They don't have to be necessarily in p orbitals in a transition state. Any orbitals, or hybrid orbitals, or partial hybrid orbitals, as long as the 6 electrons interact with each other by whatever orbitals, and they all know of each other in a cyclic array. Then it mimics benzene. 2 others that you probably never thought of comparing to aromaticity are these 2 that we've seen. Osmium tetroxide addition to a double bond. There are 6 electrons, 2 from here, 2 from here, 2 from here. In ozone, adding to a double bond, that's the first step of the ozonolysis. Remember, it's initially addition of O3, and then the ring opens, and it goes on, and eventually makes the carbonyl compounds that we get from ozonolysis. But the first step is 2, 2, and 2. This one is actually a lone pair, okay? But they're all involved in a cyclic array. Okay? And so they're all aromatic, cyclic, aromatic transition states. So from benzene, we can go on to polybenzenoid hydrocarbons, and there are hundreds and thousands, and actually tens of thousands of them, many of them occurring in the Earth's crust and coal and petroleum and so on. And that's a very hot area of investigation that has undergone a tremendous renaissance in the last 20 years because of electronic materials. Because benzene and guys like this are stabilized analogs of the polyenes that we discussed in past lectures, where we said we can get conductivity. But for practical reasons, polyenes are too unstable to be used in devices. These are way more stable, and they still have the property of a smeared out pi electron cloud. So the first one is if you fuse 2 benzene rings to each other, they share a double bond that's called naphthalene. Naphthalene is aromatic. If you look at the structure, it's got essentially the same bond length, slightly desymmetrized because the molecule is not symmetrical. So this bond is slightly different from that one, and slightly different from that one. But they're all around 1.4 angstroms. All the bond angles are 120 degrees, more or less. You can compare this to butadiene. If you just look